Hey everyone, I'm John Patinos. I'm a project manager here at the C2 Smart Center. Just a heads up that this webinar will be recorded and, like our other webinar series, posted to the C2 Smart YouTube channel for future viewing. We'll have some time for questions at the end, so if you have any questions, please type them into the chat box at the bottom of your screen, and I'll read them to the presenters at the end of their presentation. Today we're with Professor Semiha Ergan. She's an assistant professor of the Department of Civil and Urban Engineering, and also the Computer Science and Engineering at New York University, here, of course, and an associated faculty at CUSP. And she also leads the Building Informatics and Visualization Lab, that's BiLab, and she also is a director here at C2 Smart. So, Professor Ergan, would you like to introduce Zhengbo and your presentation?
Yes, thank you for the introduction. Hello, everyone. Today, we will be presenting about an ongoing C2 Smart project and where we are at in terms of this project. The majority of the presentation will be done by Zhengbo Zhu. He's one of my PhD students working on in the lab with me for the last 3.5 years. He's about to graduate. And he has been leading this effort in relation to development of virtual reality environments and integration of sensors for this particular project. So what we will do today is I'll basically introduce the overall objective of this project and where we are at, and Zhengbo will take the lead on giving the technical details of the implementation for this particular project. So with that, I'd like to start saying that this is the second year that we are working with C2 Smart on this work zone safety project. So the overall objective, the project is focusing on understanding workers' behaviors at work zones for transportation projects and how their behaviors change when they receive safety notifications from different alarming systems and devices. As we all know that there are different rules and regulations for defining work zones for horizontal construction projects. There are so many restrictive measures. New devices are being used for warnings and sharing notifications with the workers to reduce work zone injuries and fatalities. But still, these things are observed at highway construction projects. And one of the reasons for these is workers keep ignoring alarms and notifications that are sent through these devices. So this project particularly aims to understand what are those key parameters that play roles in defining the behaviors of workers in response to those notifications. And one of the key questions that we're trying to answer is, under what conditions workers ignores or respond to those warnings when they receive them at the work zones, how we can calibrate those notification systems for getting responsive actions from these workers, and under what modalities and frequencies we should be pushing these notifications to these systems so that workers are more responsive and act on when they receive those notifications. So in a nutshell, we cannot put these people on real danger zones and try to see how they behave. That's why technology comes into picture. So we work on answering these questions through integration of wearable sensors and hardware in the loop component, where we basically get realistic representations of real traffic data and bring all of them into a virtual environment to test under different scenarios and collect responsive behaviors of these workers. One of the extensions of the initial project that we propose is bringing in hardware in the loop component so that we can simulate realistic traffic scenarios through simultaneous interactions with variety of vehicles and sensor data and bring all of them into virtual environments. One of the ways we are collecting these wearable sensors is we are integrating a smartwatch where we can basically push notifications in form of vibrations and sound in the virtual environment. And we also plan to collect some physiological data of these workers as they're working in the form of heart rate variability. So we will basically eventually collect all this data from a large cohort of workers in virtual space, and I use these data to learn about the behaviors and come up with some reinforcement learning models to see how we can predict better their behaviors. So with that, I'd like to switch this to Zhengbo so that he can give where we are at and how we basically integrated all these sensors and came up with these virtual reality platforms. Zhengbo?
Yeah, thank you, Dr. Ergan. Good morning, everybody. So this is Zhengbo Zhou, and I'm working with Professor Ergan in Biolab. It's an honor to present this project that we're conducting with the C2 Smart Center. So like Dr. Ergan just introduced, the main goal of this project is to understand how can we optimally push safety alarms to construction workers that are on work zones so that we can minimize the probability of having an incident on site. So in this presentation, I will talk about why do we need this project and how are we addressing the current problems that are existing in the current efforts in addressing how workers should be alarmed about dangerous situations. And then I will introduce a framework of developing VR and body area sensor to monitor worker behaviors. And then we'll talk about some kind of next steps that we can take to take this project even further, and followed by the conclusions. So workers are in danger of work zone incidents. So some of the very common scenes that we see at work zones, for example, this one is the sensor installation on the BQE highway. So the workers are just cutting a piece of concrete there and then embed the sensor and then basically redo the surface. So there are many work zones existing, not only that one, but some kind of water main or piping in our neighborhoods. So there are work zones existing everywhere we turn, but very sadly, the construction industry is the deadliest industry in the US. On average, 3 construction workers die every single day from 2013 to 2018. And we know that about half of the crashes occur are either within or adjacent to the work zones during the construction period. And previous studies has also shown that the crash rate actually increases when there is a work zone present on the road, and the rate basically decreases after the construction is done. So apparently work zone, the presence of work zone is a huge problem in terms of worker safety and driver safety. So that's what we're trying to focus on. We need to mitigate the incident rate on work zone. The current alarming mechanisms are ineffective due to a couple of reasons. So there are 2 main categories of alerts. One is directed to drivers and the other one is directed to workers. So some of the driver focused alerting systems are workers are wearing high visibility apparel, and there are all kinds of signs informing the drivers of upcoming work zone, how long the work zone will be, and how you can best control your speed, safely pass the work zone. So, and another method of mitigating the work zone risk is we have this, Federal Highway Association has this very structured work zone design that are basically designed to minimize the occurrence of work zone incidents. So far away from the actual work zone, there will be some kind of traffic mitigating device. You can then change either close lanes and switch lanes, basically give the drivers a heads up of what's coming in front of them. And that is on the driver side. So There are also some technologies implemented on the worker side. So first, there have been development of screaming cones. Basically, there's sensor at the end of the cones, and there's a blaring horn on the other side. So when the cone you see on the picture, it detects upcoming traffic that is coming too close to the work zone structure or work zone perimeter, it will then blare a large sound to the workers, and then the workers will be noticed of upcoming dangerous situations. So some other technologies include there has been a development of safety helmet. Basically, it's the same thing. There are some additional sensors on the perimeter of the work zone, and then when the workers are wearing these safety helmet, they can then get noticed when there's upcoming traffic basically invading the work zone perimeter. But these are, a lot of them are sound-based, basically blaring horns or large noisy sounds into your ears. But something we always see is like this. So the workers are working in a very noisy situation, so they put on headphones or personal protective equipment, basically to protect their ears. So apparently, the sound-based alarms are not that effective. Another reason is these alarms are also very frequent, and the workers get used to the frequent alarms, and they basically just ignore them whenever there's an alarm, because 99% of the time they are false alarms and there's nothing's going to happen. So how we are trying to address this problem? Right now in the industry, there are some kind of vibration-based alarm system with biometric sensing. The one that we are seeing here is a offshore operation alarm system. So basically, if you're doing like oil offshore plants, basically you can have this kind of very advanced technology. So it has a chest-worn sensor, and it can vibrate. Basically, the chest-worn sensor will detect your heart rate and your basic physical metrics. And then whenever there's a dangerous situation identified by the system, it will vibrate. So it will tell you, okay, there might be some upcoming dangerous situations. But there are some limitations for this. First, it's very effective in offshore operations, but it's very expensive, and also it's cumbersome to wear. To strap something on the chest, as you see, as this person is seated, it's not a big deal. You can still be comfortable while you're working. But in traffic work zones, we're moving all the time, and we are bending our body all the time. So it's not that comfortable to have a chest-worn sensor all the time on you. So apparently a wrist-worn will be safer and easier to deploy. And that should be some kind of direction that we should be going into. And so we also know that from the studies in neuroscience and physiological studies, we know that our bodies have some kind of reaction when we are under a dangerous or a situation, or when we're nervous, or when we are under stress. So one of the signs of that is we have an elevated heart rate. So when we perceive ourselves in danger, our heart rate spikes up. And this kind of phenomenon actually can be monitored by a PPG sensor that can monitor our heart rate activity and heart rate variability. So this is very simple to deploy. It's a wrist-worn watch, similar to Apple Watch, but it's a lot more accurate. So this is where we're trying to go. We basically want to send the alarms to the workers by having something vibrating on their wrist. And also in the meantime, we want to understand how they were feeling by putting a PPG sensor on their wrist as well. So that takes us to our vision. We basically have a 3-step approach. first one, we want to create the work zones in VR because we don't want to put the workers in actual danger. And also, VR is very versatile. We can change things in VR and we can make them very realistic. So the next step would be conducting the user studies in VR. And once we have the data collected, we can then start to monitor and analyze the user behaviors based on the data that we collected. So before everything starts, we need to identify. So what kind of work zones are more prone to accidents or incidents? So basically, we concluded a couple of work zone characteristics that can be affecting the incident rate. So one of them is location type. So we have urban freeway, intersection, or some rural highway or interstate highways, right? So these different locations can have a drastically different work zone incident rate. And also the work zone duration. So if it's a mobile work zone, a short-term or a long-term work zone, so the one that we saw earlier with a very structured work zone, it's almost always happening on a highway construction with a long-term construction plan. So everything's planned out before, and basically the workers are well protected in that work zone. But a lot of the times, there are just workers doing some mobile work. They basically, drove a truck and then get their equipment out, put some traffic cones on the road, and then they just do their work in like less than an hour, and then they just leave the site. So that's a very mobile work zone, and sometimes we can see it has a higher rate of incident when it comes to work zone incident. So another important factor is the construction work type. So we have different works being done. We saw the sensor installation. Workers tend to do surveying in a very short period on the mobile work zone. And also there are a lot of longer duration work zones for like resurfacing, or you're piping or doing water main, that kind of works. So based on this information, we can then go to the real world and then collect some data to create our VR environment, right? So the VR reconstruction is really just a two-step approach. We first go to the site we wanted to represent in VR, and then we use a laser scanner to collect a point cloud representation of the real work zone scenario. So we'll introduce how to operate the laser scanner a little bit later on, and how the point cloud is collected. But basically, it's just like autonomous vehicle. You have that LiDAR sensor on top. It rotates all the time and takes in all the information surrounding the LiDAR sensor. And then you have this dense cloud of information of your surroundings, basically. And then we can take that point cloud data into a game engine. We can then develop the work zone basically in the VR with a very real representation. So given we have the VR environment, we can then enable some worker activities and traffic simulation. So we first observe the traffic pattern in the actual work zone in the real world, and then we can take it to some kind of simulation engine, for example, Sumo. And then we have some simulated traffic embedded into VR. And finally, we will design some worker tasks for them to perform in VR while they are receiving this kind of safety alerts. So the alerts are being sent first to a cloud server. Basically, the server maintains a queue of upcoming alerts, and then it will decide, what kind of modality we want to send to the worker, and what frequency we want to send to the worker, and at what time we want to send the alarm to the worker. So when the worker receives the alarm on their wrist, they also have a choice of, either dismiss the alarm by simply ignoring it, or you can just read or interact with the alarm, know what's going on, and then you can basically go to a safe area. So that's the overall vision. So I'm going to go into details of each one of these. So the first process that we need to focus on is to identify the key factors contribute to work zone incidents. So work zone characteristics, as you see in this chart, is really just one of the factors. We have a driver factor, environment factor, and road characteristics also being the key factors contribute to work zone incidents. So these are from literature reviews from previous studies. So for example, for on the driver side, the gender, age, aggression towards workers, distracted driving, driving under influence, those are some kind of common factors that are influencing the drivers. So that leads to work zone incidents. For environment, we have the lighting condition, weather condition, and the time of the day. So they are all very important to factors. The road characteristics, we have the road type, number of lanes, pavement condition, and the traffic volume. So, and finally, on the work zone characteristics, we discussed, we have the work zone activity, work zone location, duration, and the general dimension of the work zones. So after identifying these key factors, we basically can select what kind of scenarios that we wanted to implement in the VR, because we want the most dangerous scenarios that are so that we can achieve the maximum effect basically by mitigating the work zone incident. So we then selected 3 scenarios based on the key factors we identified from the literature review, and also some kind of news stories broke out based on worker fatality or worker injuries recently. So there are 3 scenarios. The first one is putting traffic barriers to set up a construction perimeter at an urban intersection. So basically what's going on is a lot of the times we're having this mobile work zone, and the workers are just gonna put traffic cones from their truck onto the road to set up a traffic perimeter, so to curtail sort of the traffic volume and flow. And that is apparently a very dangerous situation. So that's one of the scenarios we're simulating. The other one is surveying the road at an urban intersection. So this one is also a mobile work zone, and without a very well-structured work zone structure. And the workers are basically on the move. So they sometimes cross the road, they stay at a location at a very short period of time, and it can lead to some dangerous situations. And the third scenario is installing sensors on the side of the road on an urban highway. So this is based on very recent development of the sensor installation on the BQE bridge. So we have workers. This is more of a very short-term work zone that has a sort of structured work zone perimeter. So traffic cones were put beforehand, and there's some heavy equipment involved, and workers are well protected in this work zone. But because it's an urban highway and the traffic volume is really high, so we know that this is a very dangerous situation as well. So how do we convert the physical work zone to a VR environment? We have a real life work zone, and then we have this in the middle, a laser scanner. So how it works is basically there's like a rotating mirror that can reflect a laser beam onto the surfaces of the real world objects. And whenever there's a reflection from that surface, it will come back to the mirror, and the mirror will then transmit the data into this laser scanner to know how far away that point is, and where inside this 3D coordination system that point is. And also sometimes we have color information coming back. So basically, this is very similar to what we've seen on autonomous vehicles on the top. So there's something rotating very fast, and then it knows its surroundings. And what we used is a terrestrial laser scanner. It's not equipped on a moving car. We just take the laser scanner at different locations at different times, and then we combine the scans into one giant 3D point cloud environment. So what we will get is something looking very similar to the right. We have a somewhat densely point cloud capture of the real work zone. And then what we can do to convert this point cloud into a VR environment. So basically there are two approaches. The first one is called scan to mesh to VR. So the scan can actually be created into some kind of mesh. So if you look on the right with the mesh enlarged, the points can be linked into smaller triangles to form a surface. And that surface can be representing the real world surfaces where the 3D point cloud was collected. But a lot of the times, as you can see in the middle, there are surface missing because there were not that many points collected at that location, or there might be some kind of error when you are doing this automatically. Even with the state-of-the-art computer vision algorithms out there, it's still not perfect. And a lot of the times, if you let it just work automatically, you will be encountering some kind of weird errors that you did not plan. So another way is from the point cloud, we have the scan to measurements to VR. For example, we are very interested in how wide is this road, right? We can then take measurements in the point cloud by hand cherry pick the points that we wanted to use. So you can then take multiple measurements and then just get the average value of that road. You can take at different locations so that you have a comprehensive representation of the road structure. So this is because it's more manual, so a lot of the times it's more accurate for the object of interest, but it takes a long time. But at the end, we can implement those measurements into the VR environment, and then we have a more accurate representation of the thing that we are really interested in. So the three scenarios that I just talked about, we have, they are all real cases. So the first one is at Myrtle Avenue, close to campus. So the second one is on J Street. It's resurface of the pedestrian walkway. So we have that implemented in VR as well. And then the third one is on the BQE highway. So we also created the VR for that one. Right now, it's just a demonstration of how the virtual reality is looking like when we implement this in VR. So as you can see, we can basically map everything to a very realistic scale. And whenever we're putting subjects into that virtual environment, they can have a very high level of immersion. So now that what we're really caring about is how can we simulate the traffic very accurately inside the VR environment so that we can implement this later on. First, in our project, we conducted a traffic simulation in Zhengbo. So we basically download the OpenStreetMap and then make some assumptions with calibrated real-world traffic so that we can simulate the traffic pattern and volume, vehicle position, vehicle type in Zhengbo. After that, so basically I took the mean vehicle volume and speed from Zhengbo to implement that in the VR environment. So this is a bird eye view of the first scenario in VR. So we have a couple of cars basically moving within the work zone, and the traffic is traveling in the direction of the red arrows. And the work zone is in the middle. So basically I took the mean traffic volume and speed as a real representation of what the traffic should be looking like on that part of the road. And after that, we have to implement some user interactions inside VR. And the user interactions are handled by the input device. In our case, it's basically two handles that you can grab that can be recognized in VR. So we need to focus on some kind of fidelity so that the users can feel realistic when they are in the VR environment. So the first one, between user and the input device, we need to focus on the mechanical fidelity. And there are two kinds. First one is kinematic representation. The other one is, oh, I'm sorry, this is an error here. But basically, we wanted to focus on two things. So whenever the user is basically turning their heads, they should be seeing a field of view change inside the VR environment. And another one is when they are grabbing something in the VR environment, they should see that objects also being grabbed or being released. So whenever you have a very free movement inside VR to translate into the input device, the users will feel a high degree of realism inside the VR environment. And from the input device to the VR, we need to focus on the input fidelity. So it depends on the input precision and delay, and a lot of the times it's very dependent on the hardwares that we're using. So basically, the only thing that we can make sure of is we use the state-of-the-art hardware. So the best VR headsets, the most powerful computer that we can find, so that we can drive the frame rates up, and then the user don't feel there's some kind of delay between their input and the VR response. So the worker activities that we are embedding in VR are different. So here I'm just going to show you the example of the first scenario. In the first scenario, we're asking the workers to set up a work zone perimeter in the VR environment. So basically, you just come off the truck and you have a couple of traffic cones unloaded from the truck. You want to put the traffic cones onto designated locations so that you have a safer environment to work in. Basically, you can see here, the right circle is where the traffic cones are, and the designated locations are represented in the yellow glowing sphere. And whenever you put a traffic cone in that designated location, the sphere will turn green to tell you, okay, you've done this location, move on to the next one. So to see it in a flowchart, basically we have 6 cones, and we iterate in our environment to see, are all the cones being placed? So if not, then the glowing sphere will continue to glow, and the users will continue to experience this VR simulation. And until all those spheres are being filled, the locations are being filled, the simulation will not end. So the mechanisms that we're using to send alarms to workers is done through a smartwatch. Basically, we have the VR environment simulated, and we have the traffic coming in the VR environment. So we implemented 2 types of dangerous situations. The first one is a speeding scenario. Another one is invading of the work zone perimeter. So by speeding, I mean, if the vehicle is speeding more than 20% of the limit traffic speed at the work zone, then we are sending a speeding alarm to the workers on site. And if the driver is directing the vehicle to the direction of the work zone and coming in too close at a distance, we say there might be an invasion of the work zone perimeter, and we then send an alarm to the workers. So basically, whenever we have a vehicle approaching the work zone, we know what the speed of the vehicle is, and we can then send a HTTP request to a cloud server. We can then add the alarm into a queue. If there's no existing alarms in the queue, we can then just dequeue the first alarm. If there are existing ones, then we, of course, pop the first alarm from the queue. And then we handle the alarm by sending a notification to an application that we developed on the Apple Watch. So basically the notification will be sent to the watch, and then the watch app will randomly select kind of modality. Is it going to only vibrate, or is it going to vibrate and flash, or is it going to vibrate or flash or with a sound? So because we're trying to find out what is the most effective modality, duration, and frequency of the alarms, so we basically need to test all kinds of scenarios. So we randomly select the modality, the frequency, and the duration, and then we deliver the alarm and record the worker behavior towards the alarm. So basically the worker can either ignore the alarm, carry on their normal work, or they can interact with the alarm, so basically disable the alarm, or they can read the alarm and then decide to move to somewhere safer. So here is a screenshot of the construction task that we are asking the worker to conduct. So you can see there are shining yellow spheres, and the worker can basically move in the VR environment and pick up a traffic cone using the handle. And if there is a vehicle coming, they will be receiving alarms on the wrist, and then they can decide whether they want to proceed or stop. So it just goes on like this until the worker puts everything in place and the simulation will end. So we also demoed this at TRB. So here is our beloved Shri trying this simulation. So I just want to show you this to show how you look at it from an outsider's perspective. So you basically have this head-mounted display where you're only immersed in this virtual environment, and you have two handles that you can go and grab the traffic cones. So what's coming next? Because our study is mainly focused on developing VR and then conduct user studies, and this is really not a good timing to do in-person experiments because of the pandemic. So we kind of have to move along with the project, but without doing the actual user experiment. So one of the very exciting direction that we are trying to pursue is a traffic simulation with VR integration. So Sumo Unity integration, it really should be called traffic simulation and VR integration. So it shouldn't be depending on your platform. And what we can do here is link Sumo and Unity together. So basically whenever the traffic simulation reflects there's a movement of a vehicle inside the simulation, we can then see the real-time reaction of that vehicle inside the VR environment in Unity. And whenever there's some development in Unity, for example, if the worker decided to put up a traffic cone onto the road in Unity in the VR environment, then there should be a feedback loop to inform the Sumo simulation of, okay, now this lane is closed. You have to direct the vehicles to the next lane. So this is where we're trying to go. And basically, because of the pandemic situation, we cannot do in-person experiment, but the ultimate goal, like Dr. Ergan said at the beginning, is to improve worker safety by creating a personalized alarm system using the collected data and some kind of recommendation systems using reinforcement learning. So we have the ARB cleared, go ahead, but yeah, everything stopped. So how are we gonna do the personalized recommendation system thing? So basically we're imagining there's a reinforcement learning agent that knows what the worker did. So basically it observes the current danger level and the alarms sent to the worker. And the worker can then interact with the alarm, and the agent will know did the worker read or dismiss the alarm, and they will receive kind of a reward at the end. So if you send too frequent an alarm, then the workers might ignore altogether, then the reward will be extremely low. And if the worker actually encountered a danger, for example, the worker got hit by a car in the VR environment, the character, then the reward will be extremely low because maybe your alarm system didn't work so well. So those are all based on the assumption that we have a large amount of data being collected, and we'll move on to that phase once everything starts to roll again. So just some basic take-home message. First, what we wanted to do here is just using VR and body area sensor as an experiment platform. It's a very effective platform, but VR is not the final goal of this whole study. It's just a means to the end. And also, we learned how to turn a physical work zone into VR. So there are two methods. You can use a point cloud scan to mesh to VR and scan to measurement to VR. Scan to mesh is very automatic. It's very quick, but sometimes it's not that accurate. Scan to measurement to VR is very cumbersome. It's very labor intensive, but a lot of the times it's more accurate. And the traffic simulation in VR, we're moving towards a real-time Sumo Unity integration process later on. So with that, I'd like to thank everybody that's listening, and also Dr. Ergan, Dr. Osbey for directing this project. And I would like to acknowledge all the amazing help that we have, the team. Let me just go. So we have Susanna, Yubin, Abdullah, Junaid, and lately we added Fan to the team. So this is really an amazing collaborative effort, and I thank everyone on the team for putting their best work. Thanks.
Okay, thank you very much, Zhengbo. That was super interesting. And I'll open it up to participants now. Feel free to type any questions you have in the chat box below. In the meantime, I actually have some questions. I think this is a really cool project with a lot of different kinds of applications, not just to construction work zones. But first, so is your plan to eventually use these VR environments as like training for construction work zones?
That can be one of the applications, I think. But right now, the most immediate application I can see is we can understand how to send personalized alarms to workers. So because we don't know at what frequency to send an alarm so that the workers will not ignore the alarm.
Sure.
Yeah, so that's the most immediate application.
What other kinds of traffic scenarios do you envision simulating?
Because we selected the three most dangerous work zone environments, so those are the ones that we're focusing on. But I do see, so there are, for example, we have some urban intersections that are also having a well-structured work zone, and it can be dangerous as well because the workers need to move in and out a very crowded urban environment. So maybe the work zone is well protected, but maybe when they're leaving the work zone, that's when the most dangerous might occur. So we need to move along with a lot more traffic scenarios.
And what other kinds of worker tasks do you envision simulating? So this is the cone demonstration. Do you envision simulating others?
Yeah, so in the three scenarios, the second scenario is we do surveying at an urban intersection. It's also a mobile work zone. So we identified that as a very dangerous situation. And because we have the BQE highway project going on, so that is a very interesting project that we can see. So we are testing, installing sensors on an urban freeway and also calibrating sensors while there's traffic going on the highway.
a perfect example of two different C2 Smart projects working together. It's the VQE testbed project and this one. Okay, I have a couple of questions from the audience now.
Mhm.
What are some anticipated issues when integrating Sumo or with other traffic simulation software?
Yeah, so I mean, because our envisioned platform is a closed loop, so it's not only from Sumo to the virtual environment, but also from VR to back to the traffic simulation. So the first link from Sumo to VR is a, a very difficult task on itself because we need to, I mean, you guys know a lot more of Sumo than me, but in Sumo, there are a lot of manual inputs that you have to decide. You have to define the vehicle type, regular speed, or you want to randomize the traffic, right? And those parameters needs to be basically transformed into a local server and then embedded into VR. So a lot of the times, the VR has a different coordination systems than Sumo, and you have to very carefully manually implement the VR environment according to the real world traffic or the road pattern in Sumo. And when we are trying to have the feedback loop from VR to Sumo, it's even harder because whenever there's a interaction inside the VR, we need to alert Sumo right away of the road being used differently. So the road characteristics just changed, and the simulation needs to change as well. And it's a constant feedback loop between the simulation and VR. There are multiple problems that we can envision.
So workers often interact with each other. Will your tool eventually be able to include different worker interactions in the simulation?
Yeah, that's a very good question. So eventually we wanted to make this a multi-user VR platform. So basically we can have people logging in from different locations, but they are being logged into the same kind of gaming or VR environment. The worker interaction is interesting because a lot of the times we can see workers reminding other ones of dangerous situations, and other times we see workers operating one of the very dangerous equipment that can be harmful to other workers if they are not in contact with other workers. So it will be a continuing effort for this project as well.
Okay, I have another question. So you've identified key danger factors. Are you looking into scenarios, or will you eventually identify scenarios that just shouldn't be allowed to happen? Like maybe construction should never be done in the rain or during certain high traffic times. Do you envision the simulation able to eventually identify those scenarios?
I don't think the study alone can have that much of a weight to persuade, the construction crew to not do some kind of construction altogether. But we can provide some kind of suggestions to the team that, okay, these are very dangerous situations and the workers tend to ignore the alarms when they are in this situation. So what can you do to improve that?
Okay, I have another question from the audience. What is the timeline for developing a scenario from start to finish? So like scanning, processing, 3D modeling, and rendering. How long did it take to develop each scenario?
Yeah, so it took a long time. So we basically, if we already have a site in mind, we can then just go to that site and do a scan. And scan, by doing a scan, I mean, we need to scan the site fully. A lot of the time it takes more than one scan in one location. So the first scenario that I demonstrated, we actually took 7 scans at 7 different locations to create that 3D point cloud. So each scan can take from 10 minutes if you're doing a very low resolution up to 2 hours if you're doing a very high resolution. So it depends on the dimension of the work zone and the resolution that you are pursuing. But just for a regular work zone with not that accurate representation, we can do maybe a day to scan the whole work zone. And then the development, it takes even longer because we need to take measurements manually. In the scanned data, we need to convert those measurements into VR environments. And a lot of the times we may not find 3D objects that are readily available. Then we might need to do some object rendering. So that takes a long time. The most difficult is to implement the traffic simulation and also the worker interaction. So it involves a lot of coding, and you need to plan out what kind of the activities you need to do. For us, it took about 2 months, a little bit more, I think, for the VR development part. Yeah, and altogether it takes about 2.5 months just to develop that one scenario.
Okay. Okay, I have one more from the audience. This is maybe the last one, unless anyone else has any more questions. I know you mentioned some difficulty arising with the incidence of the coronavirus pandemic. Has there been any, have you gotten any user feedback from your tests at TRB? Like, has anyone, I know that sometimes sickness or feeling motion sick is a problem with VR environments. Have you gotten any sort of feedback?
Yeah, so we definitely did. So at TRB, we had more than a dozen people testing this setup, actually. And one main feedback that I receive is, okay, the VR is hard to navigate when you have a limited space. So you saw we need to basically teleport inside the VR by using one of the handlers to point and then go. So you don't just walk there like you are in a real environment. You teleport to that location. And that sometimes can cause motion sickness, or somebody who's not really familiar with technology can find that very difficult. That is the most questions that got raised.
Okay, and we have one last question. How will you compensate for the behavior differences of each worker in the VR testing?
I don't fully understand what.
So I think this question is asking, like, each worker behaves differently, like in VR and in real life. And so you're trying to calibrate this, you're trying to like monitor behavior here. So are you accounting for the difference in behavior per worker when you do these analyses?
Yes, so right now the setup is for one worker to perform the work individually. So let's basically set that as a assumption. We do have multiple users to come in, to test this environment, and then we can get the worker behavior differently when they are experiencing even the same VR environment. But our assumption is, given a large amount of alarms that the workers receive and a large amount of users that we test, we can then somewhat even out the randomness inside of the worker behavior towards like the same environment. And also, given a large amount of user interactions or user decisions being made towards alarms inside that VR environment, we can then learn the user's individual behaviors, and then basically use the reinforcement learning paradigm to create a recommendation system that is personalized to that user.
Very cool. Okay, so that's all we have time for, I think, in terms of questions. Thank you so much. This has been a really interesting project, and I hope we speak again about this as you continue your research.
Yeah.
For everyone in the audience, you can check out this webinar and all of our others on the C2 Smart YouTube channel. Thank you.
Thank you, everyone. Thanks for listening.
Thank you.
Thank you.